Welcome to the session. I am Dr. S. Anusha Kathyayani, Assistant Professor in Department of Chemistry, Institute of Aeronautical Engineering. Today, I am going to discuss on one of the interesting topic, that is on nanomaterials. We are going to see what are nanomaterials and what are the applications, followed by the preparation methods of nanomaterials as well as the methods used in nanomaterial synthesis. So we are going to focus on nanomaterials and dimensionalities of nanomaterials, preparation of nanomaterials by Sol-Gel method, followed by its applications. So nanomaterials. What are nanomaterials? Nano is a Greek word. It is a Greek word, means nanos, meaning dwarf or small. So the nano, the name itself indicates the dwarf, means very small unit is called the nanos. So the materials made up of these small materials is called nanomaterials. The prefix nano means 1 billionth or 10 to the power of 9. The dia is like 10 to the power of 9. Therefore, 1 nanometer is equal to 1 billionth of a meter. So, 1 billionth part of a meter is a nanoparticle. So, the nanoparticles are the particles between 1 and 100 nanometers in its size are called nanoparticles. Nanoparticles are the particles between 1 to 100 nanometers in its size. So the nanoparticles will vary depend upon their size also. Like it depends on 1 to 100 nanometer in its size. So if we take a single walled carbon nanotube, this is a carbon nanotube into 1 lakh times gives our hair strand. Means the human hair strand is equal to 1 lakh carbon nanotubes. Then 1 lakh hair strands is equal to 10 meters wide, 1 house. So these are the nanoparticles. They are very small in size. They form a 2D structures, 3D structures and 1D and 0D structure based on the dimensionalities. So these nanoscale materials are defined as a set of substances where at least one dimension is less than approximately 100 nanometers. So they are of interest because the scale unique optical, magnetic, electrical and other properties emerge from these nanomaterials. So they are focusing more, they are showing all the application part is showing more interest in nanomaterials. So the emerging properties like electric, magnetic and optical unique properties gives us the potential for great impacts in electronics, medical field and other fields. So these nanomaterials are highly applicable in medical field, electronic field and other fields. So nanoscale. What is nanoscale? A nanoscale is defined as an incredibly small scale of measurement. It describes the object's process and phenomena that measures less than 100 nanometers. A nanometer is 1 billionth part of a meter, which means that the nanoscale is incredibly very small. The prefix nano is the 1 billionth, means 10 to the power of 9 is 1 billionth part of a meter. So it's just to imagine also it's very difficult. Here are some examples. So we are going to see the examples of 1 to 1 centimeters to 1 angstrom. So if we see 1 centimeter is like a ball, like 10 to the power of minus 2 meter, and when 100 micrometers is human hair. Here 10 micrometers is bacteria and virus. 1 micrometer is the bacteria and virus, and 100 nanometers. So it's 1 to 100 nanometer. This is the nanoparticle range. So this is the range of the nanoparticles. So 1 nanometer to 100 nanometer, mostly in 10 to 100 nanometer. This yellow color highlight is there, no? This is the nanoparticle range. So even it is less than the bacteria and the virus nanometer. Means the dimension of these nanoparticles is less than this bacteria virus is less than the nanoparticles. So here atoms, molecules come under this 1 nanometer and 1 angstrom category, means 10 to the power of minus 10 and 10 to the power of minus 9. So it is 10 to the power of 9, 1 billionth part of 1 meter. So nanomaterials. The materials at least have one dimension between 1 nanometer to 100 nanometer are called nanomaterials. So the science which deals with its properties and length scale of few nanometers is called nanoscience. So the nanotechnology. So the technology involved in the preparation, characterization and use of the properties of nanomaterials in different applications. So the application in different fields are collectively known as the nanotechnology. It is a design, characterization and production and applications of structures, devices and systems by controlling their shape and size at nanoscale. So the application part and the use of this technology is called the nanotechnology. So dimensionalities. So they are categorized into 4 different classes. One is zero dimensional characteristics nanomaterials and another is one dimensional and third one is two dimensional and fourth one is three dimensional. So they are divided into 4 categories, 1, 2, 3, 4. So zero dimensional. So in this, the nanomaterials in this class have all their 3 dimensions in their nanoscale range. So if the nanomaterial means it should have 1 dimension in their nanoscale. So here zero dimensions means they have all their 3 dimensions in the nanoscale. So three dimensions in the nanoscale. Coming to the one-dimensional material, these nanomaterials in this class have 1 dimension outside the nanoscale. 1 dimension. Coming to the 3-dimensional or the 2-dimensional, so they have 2 dimensions in outside the scale. That is nothing but here 1D, 0D, 1D, 2D, 3D. These are the 4 stages based on their dimensionalities. They have 3 dimensions outside this 3 dimension in the nanoscale range. So here 1D means 1 dimension in outside, here 2 dimensions outside and 3 dimensions outside the nanoscale. So for this, the example are the quantum dots, fullerenes and nanoparticles comes under the 0D. So coming to the one dimensional means one outside the nanoscale, nanotubes, nanofibers, nanorods and nanovoids and nanohorns come under this one dimensional category. So the other type is two dimensional category, which class have 2 dimensions outside the nanoscale. So examples are nanosheets, nanofilms and nanolayers. So this thin film sheets, nano layers come under this 2-dimensional category. Whereas 3-dimensional materials mean nothing but 3D or bulk nanomaterials in this class, they are not confined to the nanoscale in any dimension. This class contain bulk powders. So the bulk powders and polycrystals, the dispersion of nanoparticles and arrays of nanovoids and nanotubes comes under this 3-dimensional category. So the synthesis of nanomaterials. There are 2 methods for preparing the nanomaterials. One is top-down approach and another is bottom-up approach. So top-down means from decreasing and bottom-up means increasing. So in top-down approach, the material or the precursor is reduced from bulk size to nanoscale. Here, top-down means what happens? Bigger molecules are converted into small nanoparticles. Whereas bottom-up, the smaller molecules form clusters, then nanomaterials. So this is the difference between this top-down and bottom-up approach. Here, if the material is reduced from bulk size, see, this is a bulk molecule, it is reduced into a smaller molecules. So macro to micro. Macro means big to big molecules to small molecules. So examples of this approach is ball milling method or nanolithography. Ball milling is nothing but there will be a cylindrical tank with lot of metal balls inside. This bulk material is added, so they are rotated in a circular motion at a definite RPM, rotations per minute. So what happens? These ball materials like balls, metal balls present in the cylindrical tank, while rotating, it crushes or it breaks down the macromolecules into micromolecules. So thus result in the formation of nanoparticles. This is all about the top-down approach. So the coming to the next category, which is bottom-up approach. Here the matter in atomic or molecular level gets assembled. So what happens? The very from the low level, like bottom level, like atomic or molecular level, get assembled and results in the formation of clusters. So the clusters which grow to reach nano size. As we know, this atomic and molecular molecules, this molecular level comes under the category of below 10 to the power of 8 or 9. So it is very one. It ranges in the ratio of 1 angstroms or 10 to the power of minus 10. So these are very tiny molecules compared to the nanoparticles. So they assemble and form a layers called clusters, which grow to reach nano size. So they assemble and get the nanoparticles. Examples for bottom up approach are chemical vapor deposition, physical vapor deposition, and solvent method. So these are the three methods available for bottom up approach. So we are seeing the top down approach. This is the video of this. See, we can see the metal balls crushing. These are the nanoparticles. These are the balls. We can see the metal balls. These black dots are balls. It is a ball mill generally used in the industries like mechanical attrication is a typical example of top-down method. The synthesis of nanomaterials where this material is prepared not by cluster assembly. We know from bottom-up approach, this cluster formation will happen, whereas top-down, the clusters won't form here. The structural decomposition of coarse grinded structures as a result of severe plastic severe plastic deformation. This has become a popular method to make nanocrystalline materials. Because of its simplicity, the relatively inexpensive equipment needed, and the applicability to essentiality and the synthesis of all classes of materials. So this is a ball mill. These black balls are metal balls. These are the nanoparticles. So on continuous crushing, they degrade it is like grinding, coarser grinding. So they degrade due to very small molecules, results in the formation of very small nanoparticles. As it is inexpensive, this method is used because of its simplicity and because we can synthesize all class of materials using this. So the mechanical physical process using milling through ball mill, the basic material is like this. So centimeter, it was converted into nanometers because on grinding, on the application of this mechanical and physical pressure, so they reduce its size like millimeters, then micrometers, finally nanometers. So based on this mechanical pressure in the ball mill, these molecules are converted into centimeters to nanometers. Its size reduced randomly because of this pressure. Then one of the method in bottom up approach is Sol-Gel method. So the Sol-Gel process involves the evolution of inorganic networks through the formation of a colloidal substance called sol and the gelation of the salt to form a network in continuous liquid phase called a gel. So first, here the preparation of the nanoparticles by this method involves the 5 steps. One is metal alkoxide with solvent, then the sol formation, then gel formation, or finally the nanoparticle formation. So from this here to get the sol, we have to go through the hydrolysis process, then condensation process and drying and calcination process occurs from this alkaline metal solvent to nanoparticle formation. So the precursors for synthesizing these colloids consists usually of a metal or a metalloid element. surrounded by some reactive ligands. The starting material means the precursor used is to form a dispersible oxide. So the metal oxide is used to form a dispersible oxide and forms a salt in contact with the water or dilute acid. So this is called the hydrolysis. The removal of the liquid from the salt yields the gel. So first what happens? Precursor when reacts with the water, then it forms a salt. So to on removing the salt, then it forms a gel. And the salt gel transition controls the particle size and the shape. So the next step is calcination. The calcination of the gel produces the oxide. Here this is the precursor plus solvent, means metal oxide plus solvent undergoes hydrolysis here, causes the salt formation. Again condensation here results in the gel formation. Again, so drying or calcination happens here. So if it is supercritical drying, then aerogel formation. If it is thermal drying, then zero gel formation. If it undergoes freeze drying, it forms a cryogel. So the final product is this. So it undergoes different types of drying process based on the application we are using. So the final product is this. And step 1 is hydrolysis, then condensation, then aging and drying. So this is the whole process of sol gel process for synthesis of nanomaterials. So the in detail we are going to see the step by step. How we can prepare the preparation of salt. Means precursor plus here precursor plus oxides, metal oxides or solvents. Solvent plus oxide gives salt. So the metal oxide, in this method metal oxide is used. Suppose MOR is metal oxide is used as a precursor to synthesis nanoparticles of a metal oxide. So the metal oxide is dissolved in alcohol. Alcohol is nothing but a solvent and then water is added under acidic, neutral or basic conditions. So hydrolysis has to be done with the precursor plus solvent. Here hydrolysis then results in the formation of salt. So this is the metal oxide plus alcohol gives plus water gives rise to metal oxide plus ROH. So hydrolysis happened. Then the conversion, now salt formed. So the next step is the conversion of this solution to gel. The polykondensation reaction means condensation is nothing but the removal of some small compounds. So the two compounds like first formed salt and the another compound reacts and removes the any small particles. Suppose here the water molecule. We are removing the water molecule. In the first step, we added water for the hydrolysis process. In the next step, which is condensation, we are removing the water molecules, which results in the formation of gel. So the polykondensation reaction between MOH and MOR results in the formation of an oxide or alcohol or bridged network gel. Why? Because the condensation reaction, it goes and binds with the another compound, removes the water molecule. So by removing and forming the bond, it forms a network which is called a gel. The network gel formed here is an oxide or alcohol or oxide or alcohol or bridged network. So it forms a network like structure because of the bonding between the alcohol and the precursor means metal oxide and the this bridged network gel. So MOH plus ROM gives rise to M with the bridge bonds are formed between this. This is the gel, network gel plus ROH which is removed from polykondensation. So the gel undergoes the drying or calcin process, then these nanoparticles are formed. So next step involved is the aging. Now we got gel. So we are moving on to the next step which is the aging of the gel. So the reaction mixture is allowed to continue polykondensation reaction until the gel transform into a solid mass. We are allowing the formed network like bridge structures to until means the polykondensation reaction has to be continued until the gel transforms into a solid. So this is like evaporation of the solvent. The solvent which we used in the first step, like precursor plus solvent we have used, then hydrolysis, then salt, then water, that condensation process. So the solvent is continuing from the first step. In this aging of the gel, we are removing all the solvent molecules. In the second step, at the condensation process, water molecules are removed. Now here we are removing the solvent. Whereas in the second step, we removed water molecules. Then here we are removing the solvent from this gel. Then removal of a solvent and or drying of gel. So the solid mass obtained from this process is moving to the next step where the water and other volatile liquids are removed from the gel network. If isolated by thermal evaporation, so the method, if we are isolating or removing the water and gel from thermal evaporation, the resulting product is called a zero gel. If the solvent is extracted under supercritical conditions, resulting product is aerosol. So if it is thermal evaporation, then it is called zero gel. If it is supercritical evaporation, then it is called aerosol. So it depends upon the process we used for evaporation. This is zero and aerosol. Heat treatment. The sample obtained is calcined at high temperature. So the finally obtained sample, whether it is zero gel or aerosol, is calcined, means heated at 800 degrees centigrade to obtain nanoparticles. This is our final product. So the nanoparticles formed from this sol-gel method commonly have a size of 1 to 100 nanometers. So this is the reaction. Here precursor plus solvent undergoes hydrolysis. So here sol formed, then dehydration reaction or polycondensation reaction, then gel formed. So again here removal of solvent and aerosol, then drying, aerosol. So this, if it is supercritical drying, then it is aerosol. If it is thermal drying, then zero gel. So again calcination at 800 degrees centigrade gives dense ceramic. If from the without this reaction from the sol, if spinning happened, then on a layer thin film coating, then it is thin film coating. If from the sol this calcination if we done without removal, then the powdered crystal will be formed. So both all are nanomaterials, but the application is different. So what are the advantages of sol-gel method? The main advantage of the sol-gel process are the high purity of the product, the narrow particle size distribution, means the uniformity of the size in all the nanoparticles, the achievement of uniform nanostructure at very low temperature. So what are the disadvantages? Coming to the disadvantages view, the cost of the raw materials may be high. So only one disadvantage is the materials which we are using will have higher cost. Application by sol-gel method. The materials obtained from sol-gel method are used in various optical, electronic, energy, surface engineering materials, biosensors, pharmaceutical and separation technologies such as chromatography techniques. So this they are varied applications in different fields. So this sol-gel method is preferred because it can be carried out low temperatures and the high purity of the product, and the nanomaterials obtained from this process will have the uniform size and distribution is uniform. Another method of nanomaterial synthesis is chemical reduction method. So in this method, metal precursor can be used such as metal salt solution is treated with a suitable reducing agent followed by a capping agent and the metallic nanoparticles are obtained. So after further treatment and drying, nanoparticles of metal are formed if it is a bottom up approach. So the sol gel method is a top up. This is bottom up. That is top to bottom approach. The synthesis of silver nanoparticles by chemical reduction method. So, for example, here we are heating the metal salt solution, then reducing agent was added, followed by a capping agent, then the metallic nanoparticles are formed, which on further process of drying, we get powdered form of follow nanoparticles. Here, this is metallic salt solution, same capping agent. And another example is copper sulfate. Here, the copper sulfate solution is a metal solution used. Then hydrogen hydrate is the reducing agent, and copper nanoparticle colloids are formed here. And here, the capping agent is aniline. Then and thus formed colloids are 50 degrees centigrade. Drying has to be done in a vacuum oven for 5 hours. Then the copper nanoparticles with less 1 to 100 nanometer nanoparticles are formed. Another example is the silver nitrate solution is here AgNO3. The silver nitrate solution is the precursor. We react with the and hydrogen hydrate as a reducing agent, and sodium docyl sulfate and citrate of sodium are used as a stabilizing agent. The reaction is carried at room temperature. The transparent colorless solution converted into a characteristic pale yellow. Here we can see characteristic pale yellow and pale red color followed by pale red color. The occurrence of color indicates the presence of silver nanoparticles. So as the reaction proceeds, the nanoparticles formation happening means the color of the solution will turn to different colors. So from colorless to yellow, yellow to red color. So once color this silver red colored silver nitrates are having small nanoparticles here. These are the nanoparticles. This is the culture. This is the this thus obtained nanoparticles are purified by a centrifugation process to remove excess silver ions. The silver colloids were washed at least 3 times with the deionized water to remove the silver particles which are not formed as a nanoparticles has to be removed with the excess of distilled water by washing with 3 times under nitrogen steam. So the dried powder of nano-sized silver can be obtained by freeze drying process. The particle size of nanoparticles formed from this chemical reduction method varies from 15 to 48 nanometers. These are the silver nano. This is AgNO3 NPs, nanoparticles, formed from this chemical reduction method. These are the silver nanoparticles obtained from this method. Here in copper nanoparticle preparation, aniline is used as a reducing agent or cap. This is reagent in the copper preparation. The copper nanoparticles can be prepared by the chemical reduction method in which the copper salt acts as a precursor and reduced by a reducing agent such as sodium borohydrate, hydrogen, ascorbic acid are used as the capping agents. So the chemical reduction method can also be used for the preparation of different metal nanoparticles. Here copper is used as a precursor and reducing agent hydrogen monohydrate is used. Then mixing gives a color formation. We can see the color formation of copper here. This is a solution where the copper hydrogen ions will be there. After 10 minutes, then the nanoparticles are formed like copper colloids are formed. Then separation, washing and drying using the formation of copper nanoparticle powders. So these are all about the synthesis of nanoparticles. Now how it will be useful for us. So the applications of nanoparticles are nanomaterials. So materials with structures or features on the nanoscale typically will have 1 to 100 nanometers range. They exhibit unique properties like electric properties and Magnetic properties and optical properties are very unique and behaviors compared to their bulk counterparts. These distinctive characteristics makes the nanomaterials applicable to various fields. So these nanomaterials can be used in semiconductors, paints, in cosmetics, drug delivery, medicines, agriculture, electronics, automobiles, catalysis, and biosensors and medical field. So due to these properties, they have a wide application range. Coming to the first sector, medicine and healthcare, the drug delivery systems. So the nanomaterials can be designed to carry and deliver the specific drug in improving their precision, improving targeted therapy, and minimizing the side effects. These nanoparticles are used. So the drug delivery systems like magnetic nanoparticles, niosomes, nanospheres, micelles, nanocapsules, nanoshells, solid liquid nanoparticles, and dendrimers, gold nanoparticles, and liposomes. These are the nanoparticles used in drug delivery system in improving targeted therapy and minimizing the side effects, and also for improving the precision of the treatment. And diagnostic imaging. So the nanoparticles can enhance the contrast in medical imaging process like MRI, CT scans, and ultrasound. So the magnetic resonance imaging and fluorescence imaging and ultrasound imaging, photocastic imaging, these nanoparticle cells are labeled to the specific cells, and due to the imaging process we can target and we can identify the cells with the diagnosis. So in vivo tracking is possible because of labeling the stem cells with nanoparticles. So this imaging process also use this diagnostic imaging also helpful in by the usage of nanoparticles. Coming to the biosensors, these nanomaterial based biosensors enable high sensitivity and specific detection of biomolecules, helping early disease diagnosis. So, these biosensors are also useful in drug discovery and disease detection, environmental monitoring, soil quality monitoring, food quality monitoring, toxins of defense interest, water quality management, and prosthetic devices, as well as drug discovery. Moving to the next application part, electronics. So the nanoelectronics is contribute the development of smaller, faster, and more efficient electronical devices. So with the like chips, now we are getting the chips in a very nano chips that is very small, and the storage data will be very high because of these nanomaterials. The flexible electronics, they enable the fabrication of flexible and transparent electronics such as flexible displays and wearable devices. So in the chip formation and the circuit formation, these nanomaterials of very small size are used. Coming to the energy. So the energy storing devices like solar cells and energy storage devices like solar cells, we will use photovoltaic cells generally. They enhance the use of these nanomaterials in these cells enhance the efficiency of solar cells by improving the absorption from the sunlight and charge transport, and to store in the battery. These nanoparticles play an important role. Coming to the next, they are used in batteries and supercapacitors to enhance energy storage, and charging and discharging rates will be high for energy storage devices with the use of these nanomaterials. Moving to the next, catalysis process. These nanomaterials provide a high surface area leading to improved catalytic activity. So the surface area to react for the chemical reaction, they provide these nanoparticles provide high surface area. This improves the quality of the reaction and the catalytic activity of the chemical reaction. This is crucial in industrial processes and environmental remediation process. The next application part is material science, the strengthening of the materials. Incorporating nanomaterials into these mechanical and thermal properties of materials increase the the incorporation of these nanomaterials into that substances increases their thermal and mechanical properties, leading to stronger and more durable products. Self-healing materials. Nanomaterials are generally used to develop the materials that can repair themselves when damaged. So, when it got damaged, they should repair themselves and they should heal themselves. So, in these self healing materials, like These nanomaterials causes the self-healing materials. Next is environmental remediation. These nanoparticles and nanocomposites are used for efficient removal of pollutants and contaminants from water. The air filtration. So nanomaterials are employed in air filtration system to capture and remove the harmful particulate matter. Generally, alumina granules of small balls are coated with the nanoparticles. Then water is or the pollutant water is passed through this is the column. So they have alumina balls with coatings of nanomaterials. So the water is passed, the contaminant water or polluted water is passed through this column. So the nanoparticles present on the alumina surface grasps or absorbs the contaminants present in the water. We will get the pure water. So it is also useful in the water filtration system. Coming to the air filtration, so employed in air filtration system by capturing and removing harmful particulate matter from the air. Moving on to the textile industry, the smart fabrics. Nanomaterials are integrated into the textiles to impart properties like water resistance, UV protection, and antimicrobial activity. So, by the incorporation of these nanoparticles into the textile industry, gives the UV resistant, UV and water resistant, and antimicrobial activity clothes, fabrics that are called smart fabrics. Sensors in clothing. The nanoscale sensors embedded in fabrics can monitor physiological parameters and provide health related information. Coming to the food and packaging industry, the food packaging. The nanomaterials are used in food packing to enhance the barrier properties, delay spoilage, and monitor the food freshness. Food safety. These nanosensors can detect contaminants and pathogens in food, ensuring safety and quality. The next session is aerospace and automotive. They will use the lightweight material. These nanomaterials contribute to the development of lightweight and strong materials, improving the fuel efficiency in vehicles and aircraft. These nanomaterials also increases the durability and strengthen the compounds used in the aerospace and automotive industry. One of the category in this aerospace and automotive is coatings. These nano coatings provide a protection against corrosion, wear, and environmental degradation. So these are preferred in aerospace and automotive industry. And last one is the consumer products. Cosmetics. The nanomaterials are used in cosmetics for improved UV protection, enhanced drug delivery in skincare products, and better color dispersion. So coming to the electronics, nanomaterials contribute to the development of smaller and more efficient consumer electronics. So this is all about the applications of the nanomaterials in different fields, starting from medical industry to the food industry. It's important. The important thing to note that while nanomaterial offer numerous benefits because of their unique and potential properties, their potential environmental and health impacts are also subjects of ongoing current research. They are also has to be considered. So ethical and responsible use of nanomaterials is crucial for ensuring their safe and sustainable application across various industries. So here all about the nanomaterials, synthesis and the applications in different fields or different industries. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.